Hi, I have been doing a small test with a neural network and the MNIST database, which consists of a dataset that contains numbers as they are written by humans, so handwritten numbers. And as you can see, I can probably enlarge it somewhat. Those numbers differ in consistency or neatness, or how would you say it? The point is that for us humans, it's easy to see that these are all zeros, these are all ones, and these are all twos, etc., etc. But part of the challenge is to have a neural network learn these handwritten characters and then say, well, this is a zero, this is a one, this is a two, however they are written. So this is the data set that I used. If you like more information about the MNIST database, you can find it here, Wikipedia, MNIST_database. And that brings me to the program that I made. I developed in Python with Keras. I used somebody else's work as a starting point to get me started with the model. But like I said, Keras is the centerpiece of the solution. Here I start with ASCII characters and a utility function. So to be able to display the handwritten characters on a ASCII terminal, that's basically it. Instead of doing a graphical interface, it makes it easier to use, and you can make it part of the logging. Keras has a built-in access point to the datasets, so loading data is very easy because you just say, well, load the dataset, and you automatically get a train set and a test set. And here we have the actual display of the handwritten characters, or some. I did the first 5 handwritten characters. This was what was previously there, but then you need a graphical output, and I converted that to ASCII output. Some pre-work needs to be done on the data types, because the data set has values for essentially the pixels in the handwritten characters, ranging from 0 to 255, so 255. And here the division is done to scale it to, like it says, from 0 to 1. The output labels say something like, well, this is a 7, this is a 6. But by using these utilities, you make it categories where you essentially make a sort of bitmap, where the first bit is for the 0, the second bit is for the 1, and one of those bits or categories is 1 for whatever label you attach to the handwritten character. So a digit that needs to be recognized as a 7 has the 7th bit on position 6, because it's 0-based indexing, as a 1. The model is this, and you get a summary here, and then you train the model, and that is what you're doing here. Anything special about that? Well, not really. I think that the most important point is that packages like Keras make it super simple to utilize your GPUs, so to accelerate your learning in the neural network and to accelerate the referencing to get output, essentially. By mistake, I also run this on a CPU only, and then the difference in speed on my machine at least was about a factor of 4 or 5. So obviously the GPU based solution was 4 or 5 times faster than the CPU only solution. This problem isn't that hard either. This is a rather, let's say, old problem. But it uses the GPU, and with a high-level package as Keras, it makes it super simple. Here the evaluation of the model is done, so whatever comes out of the model and the reference set is compared, and from that your test loss and your test accuracy can be displayed, and we will see that's about 99 or 89.9% or something. And lastly, I display the outcomes for the from the model for the characters that I also displayed earlier, so that you can see for yourself that I think a 7 is there and a 2, that a 7 and a 2 are actually seen as a 7 and a 2. So running this means this basically. I'll go back in the logging somewhat. You see some errors about not being able to register some part of the libraries, and what it says that it has already been registered, so tries to do it twice. As far as I can see, this is a benign error in the sense that the GPU is used and somewhere implicitly these registrations are already done, and then this happens when the library tries to do it again. Well, the output that we talked about, so it's about 60,000 handwritten digits in the format of 28 by 28 pixels, and if you convert that to display like this on the ASCII terminal, it looks like this. So these are just the first 5 samples of the training set. Here you see the model summary, so it says, well, I have a convolution layer, 2D, and a max pooling layer, and a sort of standard setup. And what might be good to see is that the trainable parameters are about 35,000 parameters, so the model eventually will consist, or does consist, of about 35,000 parameters, which are trained in a neural network by the GPU libraries. Here you see what I mentioned earlier, that the CUDNN package is indeed loaded. And let's see if there's anything else. Here the training logging starts, and it does that in different batches, epochs as they are called in neural network training. And here you see the accuracy, so after the first epoch the accuracy is already 88%, and then it slightly climbs towards 98.7. Eventually, and this is the accuracy on the validation set, so the training set is split up. It was in the program, I think 20% of the training set is used for cross-validation. And on the test set, the accuracy is 99.1%. And here you see the outcome. Image 0 is considered to be a 7, image 1 is considered to be a 2, etc., etc. So 72104, and if you go back, you indeed see, well, this is 72104. So as a human, we can say that the neural network is doing just fine. And that's basically it.